Hello everyone, this is Harsha from Midas IT. I'm a geotechnical engineer working in Midas, India. So very warm welcome to all of you. This session will be dealing about soil structure interaction using SoilWorks. So SoilWorks is our geotechnical software, and we will be having a discussion on soil structure interaction and how this can be helpful for the bridge engineers as well as structural engineers. We will be discussing that in this session. So this session mainly deals with the soil structure interaction and how this soil structure interaction affects the foundation design, and how this software can able to give the solution for the soil structure interaction for the problems being faced by the bridge engineers or as well as structural engineers. And basically this is the main focus area of this present webinar. And these are the main topics that will be dealt using in this particular webinar. I will be giving you a brief idea about Midas and what are the different foundations, basically the overview of the foundations. And there are different types of foundations using for different types of purposes based on the soil in the particular site. So what are the different types of approaches to to be used for determination of the springs, so that the structural engineers can able to go and go for the design, and what is the different approaches. I will be dealing with them. And then what is the lateral behavior of the piles and determination of the spring stiffnesses will be dealt. And the lateral behavior governs the design and it is a very most important parameter, and that will be dealt in this particular session. And later on, determination of lateral behavior of piles using SoilWorks. So I'll be using our geotechnical package, that is Midas SoilWorks, and using them to determine the nonlinear springs by performing PY nonlinear analysis, lateral load versus lateral displacement. And then we will be having your lateral springs, and that how that can be exported back to Midas Civil or any other structural software will be dealt in this particular topic. And then later on we will be having a numerical analysis to determine the stability of the abutment. So these are the different topics. So the very first thing is introduction to Midas. So as you most of them know, Midas is like a very very important, and it's a company which develops the civil engineering software solutions. And apart from the civil engineering software solutions, we are having a geotechnical softwares, we are having a mechanical softwares as well. And so this is the world's leading engineering software solutions and providing. And we got 6 branch offices throughout the world, and our main branch is present in main office headquarters is present in Seoul, South Korea, and we are having branch offices in UK, Russia, India, China, Japan, and USA. So at present, more than 530 developers are working in Midas in order to develop different products in civil engineering, bridge, and geotechnical engineering, as well as mechanical engineering. So these are some of the important and iconic structures that were completely analyzed and designed in using Midas products. So Burj Khalifa in UAE, Beijing National Stadium in China, Sutong Bridge in China, Reski Island Bridge in Russia, Shanghai Expo Pavilions in China, and as well as Incheon Bridge in Korea. So these are the most iconic structures, has been completely modeled, analyzed, and designed in the software in Midas products. So these are our global top 100 companies which are using Midas products. So we are having most of the important companies which deal with the very infrastructure projects using Midas products. So we got AECOM, we got Roop, we got Akidis, we got Sistra. So you can see most of the global top 100 companies are using Midas products. So this is our product line. So in bridge and structural engineering, we got Midas Gen, Midas Design Plus, and Midas D Shop. In bridge and civil engineering, we got Midas Civil and Midas FEA. And in geotechnical engineering, we got Midas GTSNX and Midas SoilWorks. And in mechanical engineering, we got Midas NFX and Midas FX Plus. So basically, today we will be having a complete demonstration using the software Midas SoilWorks, and how this software can able to have a link between for the soil structure interaction and link between your Midas Civil. So basically we will be defining and modeling and assigning properties for the bridge in the Midas Civil, and for design and for analysis we need to provide a certain soil springs, and how SoilWorks can able to give that give that particular spring stiffnesses to the Midas Civil will be dealt in this particular webinar. So this is basically a small slide about a Midas SoilWorks. So we got 7 different modules in a SoilWorks. So in SoilWorks we can deal with the slope, we can deal with the rock, we can deal with the foundations, we can deal with the dynamic structures, seepage, soft ground, and as well as the ground for tunnels, and as well as the abutment structures, the stability checks, everything. So I will be giving you 1 or 2 line description about each and every module. The very first module is a slope module. Slope module basically consists of 2 different methods incorporated in them. The first method is limit equilibrium method, and the second method is finite element method. So both this method has been incorporated in the slope module, and which will be helping in order to determine the factor of safety and stability analysis of the slope. And in the rock module, we got 2 different methods again incorporated in the rock module. The very first one is a stereographic method. So, and other one is the limit equilibrium method for rocks. And the next module, we got a foundation module. So this foundation module will help the structural engineers in order to determine this like soil structure interactions behavior, and what are the different types of springs and how that can able to be taken back to the Midas structural software or any other structural software, and then how that can be helpful for your design and analysis of this of your bridges or any other infrastructure projects. And then we got a dynamics module, and in this dynamic module we can run time history analysis, eigenvalue analysis, response spectrum analysis, and we also have underground response analysis incorporated in this particular dynamic module. And then we got seepage module as well. In the seepage module we have a steady state seepage and transient seepage analysis that can be done in here. In the soft ground module, this is completely dealing with the consolidation. So we got a 1D Terzaghi method incorporated in here, and another one is a finite element method. So this will be very much helpful to determine the behavior of the soil in your particular area when there is predominantly a clay present in your area because of the consolidation. And we got a ground module. So this is a complete finite element method incorporated tool, and in this particular module we got a stability analysis, stress analysis, or settlement analysis for your abutment, excavations, pile foundations, or as well as the shallow foundations. So we can deal all of them in using this ground module. So this session basically deals with the foundation module followed by a ground module. So this foundation module, as I said, here it is completely related to the structural engineers where we develop springs, and that springs can be taken back to the civil or any other Sophistic or any other bridge softwares. So what we basically do in here that will be dealt. So here we do PY nonlinear analysis, lateral load versus lateral displacement curves will be found out, and those springs, those curves will be acted as a spring constants like a multilinear springs in your structural softwares that will help you in finding and analyzing and designing of your infrastructure project. And later on we got a ground module. So in this ground module we are going to deal with the stability analysis of your abutment. So these are the 2 prime focus of this particular webinar. So the very first thing is that I will be giving you a very overview of the foundations. So we got 2 types of foundations, basically a shallow foundation and a deep foundation. So on combination of these 2 we got a pile raft foundation as well. So in a shallow foundation it is basically used whenever the load coming from the superstructure is low, and whenever we got very less load, like in terms of buildings or in terms of very like a very small infrastructure projects. Basically, it all depends on the soil present over there. So in this shallow foundations, we got three different types. One is strip foundation, isolated footings, or mat foundations. And based on the different shapes of your isolated footing, we can go for circular footing, rectangular footing, or square footing. So that's a shallow foundation for you. And in terms of deep foundations, we got pile foundations or well or caisson foundations. So in the pile foundations, we got end bearing pile and friction pile. So whenever we got very low density layer of soil in the very ground surface, so we need to surpass that one so that we cannot use your shallow foundation over here. So that's why we need to go for some deep foundation. So where your foundation will surpass all the low density layers and goes to the higher density or rock layer, so that the strength will be transferred from your load, your superstructure directly to the high density or rocks in the very lower layers. So that's your deep foundation. And apart from this, we can combine the raft and your pile to have a pile raft foundation. So that's the basic idea. And how the very next step is what is the process that is being done in any infrastructure project, and how that can able to have a clear view of the project, so that how the geotechnical engineer can able to help the structural engineer, and how structural engineer can himself do all the determine all the necessary structural parameters. So basically, whenever you got any project, what we do is we do the lab test and we do some field tests. So this lab test or field test may include your plate load test or pile load test and some lab tests. So based on these tests, we get some parameters of your soils. And then this geotechnical engineer, based on the load and based on the soil profile and based on the lab and field test data, he do some parametric study and he calibrates with the your numerical model with the existing data, so that he can come to have a particular geotechnical design. So geotechnical design includes your dimensions of your type of foundations, dimensions of your foundations, the spacing of piles in case of deep foundations, the diameter of the piles, everything. So this is the basic idea a geotechnical engineer can able to provide to a structural engineer. So for the structural engineer, it is his job to perform the like analysis to find the forces in your foundation, and followed by design of your foundation. So in between, we got one particular thing, that is determination of structural parameters. So basically, structural engineer designs the foundations, like calculating the rebars and everything. And so in order to calculate the rebar, we need to provide certain stiffness of your for your springs, which acts like a soil in the structural softwares. So in order to determine your structural parameters, we need to have a spring stiffness. So spring stiffness basically can be of your subgrade reaction, or your pile end bearing resistance, or your lateral spring stiffness. So your lateral springs plays a key role in terms of your design of your pile foundation. So how these lateral springs can be easily helpful for your easily determined for by the structural engineer, or how the geotechnical engineer can able to easily provide this particular lateral springs will be discussed in this particular session. So we'll be discussing about these particular lateral springs in brief in detail in this particular session. So determination of spring stiffness. So for a shallow foundations, let's say that we got an strip footing, or we got an isolated footing. So how the subgrade reaction, subgrade modulus can be determined is, we need to have an applied load. So that might be from the plate load test. So plate load test is a very very frequent approach which can be dealt by the geotechnical engineers in order to determine the resistance of the soil for a shallow foundation. So plate load test, from the plate load test you can get the applied load, or else in many cases it is impossible to go for the plate load test. In that case, we can go for the bearing pressure calculations using the Tasaki theory or basics theory or Meyerhof theory, and we can get the applied load. From the load which we get, that will be divided by the settlement criteria. Let's say the criteria for the shallow foundation settlement is 25 mm. So it should not exceed 25 mm. So that's your criteria. So that will be divided by 25 mm, and then we can find the subgrade modulus. And other approach is the Bowles approach. So what it basically do is it calculates the bearing capacity of your foundation, the allowable bearing capacity basically, and that will be multiplied by your safety factor and multiplied by 1000 by 25. 1000 is nothing but it considers the width of the footing as a 1 meter, and divided by 25. 25 is your settlement criteria. So that is 25 mm. So this is your Bowles approach. So basically for shallow foundations, we can either go for plate load test, or we can determine the bearing pressure, or we can use a Bowles approach in order to determine the springs. So that's as simple as that, and this can be easily dealt by the structural engineer itself. And when we go for the deep foundation, it is some complex, and how this software can help you to make a bridge between that complexity to the easy approach we'll be discussing in this session. So now the very first thing is lateral behavior of the piles and spring stiffness. So before going into the determination of the spring stiffness for your deep foundation, we will see what the lateral behavior and how it is of prime importance for a structural engineer to use this type of approach that is nothing but nonlinear springs in his structural design. So basically, let's say we got a deep pile, very deep foundation, and this is a pile foundation, and we got number of layers. And in the very first case, whenever you you execute your pile, the stress will be somewhat like this. Here you can see. So around your section, you will be having very uniform pressure. So but whenever you apply some lateral load, so there will be so whenever you apply very lateral load, you'll be having huge stress onto your on one side of the section, and very less stress on the other side of the section. So this is very important thing which needs to be considered, and this will govern the behavior of the pile. So let's say we have provided some particular spring over here, and we have developed one more spring, and we have developed different springs data in different layers. So this is imaginary springs, let's say. So whenever a load is applied, so this load will get dissipated through the pile, and we get one layer of soil which is having different properties with the, when compared with other layers. So the lateral load versus displacement can be like this. So it is different from the second layer, and second layer load and displacement behavior is different from third, and third is different from the fourth, as well as the load coming from top to bottom is also different. So we cannot consider same stiffness of the soil for throughout the length of the pile. So we need to vary different lateral springs throughout the length of the pile, and there are many theories in order to determine the lateral springs along the length of the pile, but they can come up with only one single value, that is nothing but your linear springs. What you basically do is you use different approaches in order to determine the linear springs, and that will be applied to different depths. But this cannot serve the further purpose whenever you go for a group foundation. So I will be coming to that particular point. So this is the basic view of the particular lateral behavior of the pile, and we got two different types of lateral springs. One is your linear springs, and another is your non-linear springs. So so in order to go in deep into the pile foundations and the group pile effect, I will be giving you a rough idea about what is the pile foundation, what are the different resistance coming onto that particular pile, and how to calculate the stiffnesses will be discussed now. Suppose let's say we got a pile, we apply a load. So this load will be resisted using your end bearing of the pile and as well as skin friction. So these arrows will be representing the skin friction, and this arrow is representing your end bearing resistance. So your ultimate bearing capacity of your pile is equal to the shaft resistance plus tip resistance. So this shaft resistance can be calculated using this formulas for clay soil and using this formula for a sandy soil. So this is one case, and for a tip resistance, that is your end bearing resistance, we got this particular formula. So these are your different formulas, and that can be helpful in order to determine your shaft resistance and tip resistance, which ultimately lead to determine the bearing capacity of your pile. And now, so you know the different resistances. So that is your end bearing resistances and as well as spring resistance, skin friction. So now we in structural softwares we need to define a pile and we need to determine its spring constant over here, and we need to define a lateral springs onto your piles as well. So how to do it, we'll see now. So in the very first case, we need to define the pile tip. So let's say we got a pile tip like a spring stiffness for the pile tip. So what we do is we determine the tip resistance, that is your QT, that will be divided by your settlement criteria. So that is your, let's say 12.5 or 10% of the pile diameter. Based on the different codes, it varies. So that's your approach in order to determine the pile spring stiffness, or else we can do it by using the pile load test as well. So in most of the cases, pile load test is not available, so we use this particular formula. And let's say now we are going to determine the lateral springs. So we are done with the tip like end bearing springs. So we are now into the lateral springs. So in the lateral springs, there are many approaches, and most familiar approach and most approach is a basics equations, and this basics equation has been widely used in most of the consultancies. So in this basics equation, what we do is we calculate the spring resistance, that is your Ks, along the depth. So we can see there is an AS and this is your BS. These two are coefficients and multiplied with a Z power n. So what we basically do is we do calculate the skin resistance that comes in the AS, and we do calculate the BS as well, and Z is nothing but along the length of your pile. So let's say at from second meter from the surface of the ground we got different soil. So for that particular soil we calculate AS and BS again, and that will be multiplied by your depth, so that you'll be having your lateral spring stiffness for your pile, and that is in terms of soil. So for soils we use basics approach. So we can't use this basics approach in terms of rocks, because it provides you with the it overestimates the stiffness of the rock in when we use the basics equation. So for that we use this particular equation. So in order to determine the Ks value, we basically use this particular equation. It basically depends on ES, that is the elastic modulus of your soil, and B, the width or the width of the beam, and Vs, that's a Poisson's ratio. So basically this particular term will be equal to 1, so that the Ks can be like whenever you input all the parameters, this particular term will be almost equal to 1, so that the Ks will equals to Es divided by B into 1 minus Vs square. So this is for rocks. So now now what we do is we got a spring stiffnesses for your tip. So using this particular formula, and then we got a lateral stiffness using this particular equations for soils as well as rocks. But these are only for a linear springs. Basically you'll be getting one particular value, and in both the cases, and that particular value will be linearly varied using the interpolations and linear interpolation, and then you will be having a linear springs. So that's one particular case. Suppose let's say we are into deep foundations and we are using a pile group. So how the load distribution or dissipation takes place, and how that affects your pile behavior will be seen. We'll be seeing it now. Suppose let's say we got a pile group. So we got a pile cap, and we got like 3 by 3 piles in this particular case. So what it happens is this particular pile group will act like an group. So this will be resisting the this will be resisting the load equals, and it will be more than the summation of each and every resistance of the pile, each pile. So the group will be acting, it means it the group capacity is very, very high when compared to the summation of the capacities of each and every pile. So that's why in most of the cases pile groups are used, and single pile with pile cap is very less used. And suppose let's say we are into a pile raft foundation. So we got a very huge pile cap, and then underneath it we got a let's say 100 piles, such a number of piles. So now in that particular case, 30% or 25 to 30% of the load coming from the superstructure will be taken by your raft, and then the rest will be transferred towards the bottom, that is your pile foundation. So in the pile cap, in that particular pile gap, so your behavior of the soil will be changing because the load coming from the superstructure is changing. So based on the type of foundation, your stresses dissipation will be different, and as your depth of your foundation changes, the load coming onto your foundation changes, as well as the behavior of the soil changes. So this is the basic idea, and yeah, now we will go further. So basically, in this case of pile group, this lateral load distribution is not similar to that of a single pile. Hence, this provision of springs does not solve this particular purpose. Means whenever you go for linear springs calculation, that does not serve the purpose when you go for pile group, because that equations are derived for a single pile and we got a pile group. So how that overestimates your particular foundation design, and how the coming approach which I'm going to deal with is a nonlinear spring, and how that can able to provide you with the correct approach. So that will be dealt now. Hence, that's why we need to go for nonlinear springs, PY nonlinear springs, using PY nonlinear analysis. So that will be dealt in this particular webinar now. So here you can see this is a particular pile. Let's say whenever this pile is like completely incorporated into the soil, that is executed, and this pile is placed in the site. So this is the initial stress concentration towards your pile. So in the cross section, it is uniform throughout. But whenever a lateral load is being activated, so your pile cross section is this, and the stress variation is like here. So because of this, we need to calculate the lateral behavior because the lateral resistance of your soil comes into picture, and we need to calculate the nonlinear springs because of the variation of your lateral load, how your behavior of the soil is changing, and with respect to it, since soil is a highly nonlinear material, how this can able to help for your like a design and analysis will be dealt now. Yeah, so in order to determine nonlinear springs, so in order to determine the nonlinear stiffness or lateral nonlinear springs for your so basically lateral springs, we need to model them in structural softwares, and for that we are going to define a nonlinear springs. So there are two different many methods basically, and now the major and main important method is a PY analysis. We can use this Brom's method as well. So this is one method, and we got a PY nonlinear analysis. So what it basically do is, it's an iterative process. It is so in this SoilWorks, we basically go for foundation module, and in the foundation module we basically do this PY nonlinear analysis, and how that can be done will be dealt in this session. So once this particular topic is covered, I will go for the demonstration. So basically we calculate the deflection of each pile segment, and depending on the deflection we calculate the resistance of the soil using this PY curve. So this PY curves has been already generated, defined by different scientists for different types of soils. Let's say we got a theory called Resetall theory and a Matlock theory. Resetall theory is basically for science, and Matlock theories for clays, and similarly we got theories from API as well, American Petroleum Institute, and they develop PY curves for different types of soil. So using these curves we calculate the stresses, and from how the stresses is calculated based on your settlement and as well as deflection. And we keep iteration to obtain, we keep on iterating to obtain an like a correct value. So this particular analysis is based on finite difference method. Now we will be using SoilWorks to determine your lateral springs, and how they are going to determine, we will be seeing it now. So in SoilWorks we got certain workflow. So like we go for different workflow in different softwares. So this is the workflow which we need to go for determination of py nonlinear strings, and we need to carry out py nonlinear analysis. So we need to go for definition of your ground materials. We need to define pile materials. So the ground materials includes your different layers of soil, and we need to define a pile materials, and then input your ground layer thickness. So what is the different thickness, and it could be uniform or non-uniform. We need to define the thicknesses basically, and what is the type of foundation and how you need to apply them in here. And we need to specify the forces coming onto your foundation, and we need to define the analysis cases and design options. So we need to execute, and this is analyzing the results. So this is a basic approach. Yeah. So this is the bridge we are going to take, let's say we got an abutment in here. This is a T-girder bridge basically. This is completely modeled in Midas Civil. And here we got an abutment, and we got a pile cap, and we got piles in here. This is a 3x3 piles, and having a diameter of 1.2 meter. And we got a piers in the middle, and we got a pile cap, and we got 2x4 piles. So basically there are 8 number of piles in the middle, and 9 piles in case of abutment. Yeah, so this is what we are going to perform. So we are having an abutment, and we are going to define the piles. So this is a 3x3 for the abutment, and we got a pier, and we got 2x4 for the pier. And these are the different layers of soils which we are going to deal with. So now we will go into the software demonstration today. So whatever queries which you have, please post it in the questions tab. So once the session is over, I will be going into each and every question, and we'll be having a discussion on them as well. So whenever you open this particular SoilWorks software, you will be having 7 modules. So this is the 7 different modules which I was talking earlier. We got a ground module, we got slope module, we got rock module, soft ground, foundation, seepage, and dynamic. So since we are interested in foundation module, so we go into foundation module now. Yeah, so as I already shown to you, this is our foundation. So this is our foundations. So we got 3x3 piles, and we got an abutment, and we got a pier, we got 2x2 piles. So this is how we are going to define the foundations in SoilWorks, and how to determine the PY nonlinear curves will be dealt to you now. And before going into it, I'll be showing you the structure model here. So this is a Midas Civil. This is our flagship product, and I think most of the clients, most of this particular webinar, the attendees are using Midas Civil, I guess. So you can have a very like whatever queries you have, you can post it in the query session. Like this is a T-girder, and we got an abutment, we got a like pile cap, we got 3x3 piles, and we got pier, pile cap, and 2x4 piles. So we just modeled the piles. We got a geotechnical design, we modeled it, but we are yet to model the springs. So your nonlinear springs, we need to model it. Actually, I already modeled, but how I have modeled, I will be showing you now. So this is the basic interface of your civil. You can go from right to left. What you do is you go for geometry, structure, definition of your node and elements, properties, followed by your boundary conditions, load application, and type of analysis, and so on. So yeah, so the very important thing now we need to do is we need to take this particular geometry. So it means we take the dimensions and we model that in SoilWorks now. So we got here, we got your 3 by 3 piles, and we got an abutment. So we are going in model it now. So the very first thing is we got piles. So we need to define a pile property now. So go to structural property. So it is very easy, and directly the structural engineer can able to use this particular software. No need expertise of the like a geotechnical engineer. So let's say we got a piles, and there are two different types of piles. Underneath the abutment we got a pile of 1.2 meter diameter, and underneath the like a normal pier we got a 800 diameter. So that is nothing but 0.8 meter. So what we do is we will define two different piles. So pile with 800 as your diameter. So what type of that, what is that particular pile type? We need to choose a cast in place pile for instance today. So what is the shape? Let's go for round. This is concrete, and the diameter is 0.8 meter. So the stiffness is automatically calculated, and this is a concrete property which we are using. We got a modulus of elasticity, Poisson's ratio, unit weight, and the particular thermal coefficient. So just press add. Now we got a piles underneath abutment as well. So go to pile and give the name as a pile 1200 diameter. So this is again a casting in place pile, and we go for 1.2 meter. So the stiffness is automatically getting calculated, and just press add. So here we got two different piles, and what we need to do is now we got a piles that has been defined, and we need to define the soil layers now. So we got four different types of soils. Let's say we got alluvial layer, we got weathered soil, we got weathered rock, and we got soft rock as well. So we need to define all these particular properties. Go to ground material properties, and what we do is we have a particular first layer with the name of alluvial soil. So what we do is we define the material properties regarding and corresponding to your alluvial layer. So alluvial layer, we choose sand over here because in most of the cases we find sand in alluvial deposits. And what is the unit weight? This will be provided by this geotechnical engineer, 18, and internal angle of friction, it's of 25. So in here, we need to choose a type of PY, like PY curve for the PY analysis. We are going to choose sandy soil from American Petroleum Institute. So let's say the ultimate skin friction is at 20, and ultimate bearing capacity is 600. Just press add. Now we have got second layer, that is your weathered rock. Sorry, weathered soil. So this is your second layer. Let's choose sand again, and 17, 19, and internal angle of friction of, let's say, 26. We got a material type resettle theory, and initial horizontal subgrade reaction, let's say 16,000, based on the formulas with equations which I have shown you in the earlier. Ultimate skin friction is 30, and bearing capacity, let's say 4,000. Add. And we got third layer with the name weathered rock. So go for weathered rock and give the unit weight as a 20, 22 as saturated unit weight, sorry, 22 as your saturated unit weight, angle of internal friction as a 28 degrees, and the subgrade reactions, let's say 43,000, because since it is a rock, and we got a skin friction of 50, and we need ultimate bearing capacity of 6,000. Yeah, and the next one is soft rock. So we can choose soft rock over here. So let's say the unit weight is 23 and saturated unit weight is 25, unit weight 23. Cohesion is of 3000. It's a rock material, so this will be provided by your geotechnical engineer. 35. We use weak rock material, and let's say the initial subgrade reaction is 14,000. 140,000 basically. And let's say the strain at 50% stress. This is like around 0.001. 000, that is 1 e power 4. We can go for 50%, right? So what is that 50%? That is 5. 300 as your skin friction and 6,000 as your ultimate bearing capacity. So this is your soil properties, and these properties will be given by your geotechnical engineer. And now we have defined the soil layers, we have defined the rock. Now we need to define the soil layer formation. So how what is the thickness of each layer will be defined now. So let's say the first layer is alluvial layer. The depth is 7. Let's say the first layer thickness is 7.7. We choose alluvial layer, and the second layer is weathered soil, and the depth from the surface is let's say 9.6 meter, and it's the weathered soil. And we got a weathered rock. We choose 12 from the top, so we go for weathered rock. And we got a soft rock. It is 20 meters from the top till 20 meters, and we got soft rock. So this has been defined, and now just press close. So go to foundation type now. So in the foundation type, so we are going to define the type of piles in here. So if using this particular tab, we can able to limit the type of your length. We can able to limit the diameter of your piles. Basically, we are going to run a parametric study for different types of layers, and within 5 to 10 minutes, the analysis will get completed. And based on the results, you can able to choose the stability. Means you can able to see the stability of your foundation, and you can able to choose which is the optimistic design for my particular pile. So that's what we are going to do here now. So as I said, preliminarily we are going to go for this abutment. The very first one is your 3x3 piles, and we'll be defining these particular parameters in the SolidWorks now. So as you can see, we are not modeling them, but we are just defining the inputs in the software. So let's say the first one is given with the name of abutment. It's 3x3 piles, and each pile is of 1.2 meter diameter. So for this particular pile, we got an pile cap. So let's say the pile cap is 6 meter, and we got length is 12 meter, and let's say the thickness is 1 meter. So if you are into some offshore structures, your piles should not be touching your ground surface. In that case, you can provide the depth or underside. Now, as I said, we are not going to define any of the offshore structures. It's for normal structures, let's say. So now we need to define the eccentricity. Suppose, let's say we got your pile. So from the center, your pile, your load application point is of like around 1.5 meter. So that's what we are going to define in the SolidWorks. So let's say the eccentricity is a minus 1.5 meter. And underneath the abutment, we are choosing a pile of 1200 mm. Let's say define number of rows as a 3. So there is no left and top distance. We are going through the symmetric thing. So equal interval of a 2, number of rows, let's say 3, and 4.5 in the x direction. So what we do is we choose the pile length as 13 meters. So as of now we are choosing the pile length as 13 meters. What we do is we choose the grid arrangement and let's say pile reallocation. So this is a 3 by 3 piles, and your eccentricity, based on the eccentricity which you have provided, your load application is somewhere over here. So because of this, you can see all the piles has been formed and load application is over here, and the equal interval of 2 meters. This is your 2 meters, and in y direction it is 3 meters. Center to center from each pile is 3 meters. So if you want to provide some batted piles as well, in that case you can provide your beta angle and the rotation angle as well. So if you want to provide some elastically restrained condition from your pile cap to your pile, in that case you can go for elastically restrained as well. So this is your particular arrangement, and let's say add. So now what I can do is I will change the name, and I want to reduce the length, and how this particular reduction in length can able to change my behavior. I want to run some parametric analysis. So let's say I want to write the name as a second trail for abutment, and let's say I want to decrease the length to only 10 meters. Let's say pile relocation and just say add. So this is your second trail. So now what we do is we got an abutment the length, and we had defined the plan view of your piles. Now we need to define for your pier and middle piles, basically pier cap, piers, and pile cap and piles. So here we got the second case. In between you can see we got your pile cap, and these are your piles. So we got 2 by 4 piles. So we are going to define them in the SolidWorks now. So give the name as pier. So we are having 2 by 4 piles. Just say 2 by 4. This is what I'm just providing with the name similar to description, and we got 800 mm diameter. And for this pier, we got for this piles, we got an footing size that is nothing but your pile cap of a 6 meter and a length of a 10 meter and a height of just 1 meter again. And now in this particular case we are not having any eccentricity, and all the load is coming onto the center, let's say. So eccentricity is 0. So we are going to use 800 mm piles, and let's say the length is 13 meter. So the number of rows is 2 because we are going to for 2 by 4 piles. This is your 2 by 4, and distance of 2.5 and equal interval of 2.5 again. So pile reallocation, yeah. After pressing your pile reallocation, your piles has been formed. The load acting position is here, and we got all the piles. So this is what we are defining, and then just press add. So let's say we are going for another piles, another analysis with the pile set of 10 meters. And this is your second trail. Just say pile reallocation. All your length will be changed over here. If you want to provide different length for different piles, you can able to change your pile length in here. Now this is your second trail for your pier piles. I'll just press add. Now close. Yeah. So I just forgot to press add. Now we will define them again. Alluvial depth is 7.7 and alluvial soil. Second one is your weathered soil. Depth from the ground surface is 9.6 meter, and choose the ground material layer as weathered soil. And third one is weathered rock, and depth from the top is 12 meters, you weathered rock. And we got a soft rock. Depth from the ground surface is 20 meters. This is your soft rock. Add. Yeah, so now you can see this is your different layers. We got alluvial layer, we got weathered soil, we got weathered rock, and we got soft rock as well. So now what we are going to do is we are defining the analysis cases. So the modeling is done. We have defined the pile properties. We have defined then like a foundation type. We have defined the soil properties, and then we need to define the load. So how to get the load? I will be giving you an idea now. So let's say we got 4 different types of foundation types. So the very first one is abutment of 12 meters length of your pile, and second one is abutment of 10 meters. So this is resting in the weathered rock. The first one is resting on the soft rock. And now we are going to like determine the P-Y nonlinear curve as well as the foundation stability as for your piles underneath the pier as well. So this is your pier 2x4 piles. This is still 12 meter of 800 mm diameter, and this is your pile of 800 mm diameter, but the depth is restricted for 10 meter only. Yeah, so now we need to define the loads. So here, so for safety, I'm going to like this is how we determine the loads, let's say. Yeah, so here I got my piles, I got my abutment, I got my pier, and I got my pier, and I got my abutment again. So this is in the structural software. So what I do is in the structural software, I am going to run the loads, and I will be getting the reactions in here, and these reactions will be taken to the like SoilWorks, and that will be acting as an that will be acting like a load. So this reactions from the structural software will be acted like a load over there. So this is a complete fixed supports, and have provided some crash barrier load, have provided a SIDL load, self weight, and some footpath load as well. And apart from this, I have provided some moving load using ASTO LFRD. And yeah, so we will run the analysis. Now we'll see the results. So I have already ran the analysis. We'll see the results now. So I have chosen auto generation, and in this auto generation, I have chosen ASTO LFRD, or you can go for a Euro. So based on your convenient, you can choose the type of your code. So what I do is I'm already having certain load combinations developed based on the code chosen. And now I have developed envelope, and this envelope is combination of all the load combinations. So if you're having your own load, case, then means a one load, and you know what is the worst load case, so you can take that load case and you can get the reactions, and that reactions will be taken back to your SoilWorks. So basically, let's say I have chosen envelope where this is like a combination of all your combinations again. So that's a combination of combinations. And just press close now. So we'll see the results. So let's say if you know that this particular combination, that is your CLCB5, is the worst combination, you can choose the results, and you can take the values directly to the SoilWorks. But in order to have a more safety factor, I'm just going for an envelope case. Let's say CBC maximum envelope, and I'm going for reactions now. So in this particular model, I haven't modeled piles, but I have only modeled the superstructure along with the substructure, but no foundation. So yeah, in the abutment location, you got an vertical reaction of 5158.9. So that is your vertical reaction. And you got 20.3 as an horizontal load, that is in y direction, and in z direction you got a 5158.9 kilonewtons. This is 20.3 kilonewton. Similarly, underneath the pile we will take the maximum load. So you got 8227.3 kilonewtons in the vertical direction, and we got 34.4 in the horizontal direction. So now what we do is we go into the SolidWorks software, go to foundation load. So underneath the abutment, we know the load. This is your abutment load. So the Vx in x direction we are not finding any forces over there, and in y direction we got 20.3 load, that is in kilonewtons, and so that is a reaction. So that reaction will be applied like a load over here. That's why we are having minus sign. And the vertical load of around minus 5158.9, and the moment, let's say minus 1.854, and we are not having any moment around about the y-axis, and let's say mz. So that is your moment about your z-axis. So I'll be showing that loads again, 0.4052. Yeah. So and again now we'll go to here. So I had chosen the envelope that is the strength criteria. Now for this particular case here we will go for moments. So this is your moment. We got a moment of 405.2 about z-axis and 1854 about y-axis. Yeah, about x-axis, sorry. So the load will be changed now. So we got 405.2. Here, this is in kilonewton meter, right? Yeah, so we will choose it as 405.2. And here also we'll change it as 1854. Yeah. So that is with respect to meters. Now what we do is we got some abutment load as well. So in the abutment we got moments like around 397.8 and 323.2, and we got reactions like 8227.3 and 34.4. So we need to like input the same parameters in here. So this is underneath the piers. And the load which we got in Vy direction is minus 34.4, and the p-value is, that is your vertical load, minus 8227.3. And about x-axis you got 2263. So we'll see it again once again. So about x-axis you got 2263.5, and about y-axis, sorry, this is about z-axis, and this is about y-axis. And let's say about y, we got a 323.2, and this is also again minus, because whatever the values which we have seen is only an reaction, so we need to apply them as a load in here. Minus 397.8. So this is your moment about z direction. So we got loads in about piers, and we got loads about abutment as well. So what we do is we just close it, and we need to go for an analysis cases. Just add your analysis case. So the very first case is, so let's say if you're having any water level, so that will be your boundary conditions, let's say. So let's say your water level is of 5 meters from the top. You go for water level. So from the ground meter, let's say 5 meters. This is your water level. Minus 5 meter. Sorry, this is 5 meter. It takes automatically. go to analysis case. So we are running the analysis and we will find the results. So in the very first case, we go for abutment 3 by 3 of 1200 mm, and we got water level, and abutment underneath we got an, so this is a load set which we have defined with the name of abutment. So this is your first trail for your abutment case. Just press, so you can choose your convergence criteria. Let's say press apply now. And let's say second trial for your abutment, instead of your foundation type 3 by 3 of 13 meter length, I'm going to choose second trial here. This is your abutment of 10 meter length. Let's press apply. And now we will choose the first layer, first trail for your pier. Let's say this is a pier of 2 by 4 meter and the length is 13 meter, and the load coming onto your piers is a pier load and not abutment. Just apply this like that. Similarly, change the name to second trail. Here choose the group as second trail pier. Now press OK. So we got all the 4 cases. What we do is we will run the analysis, and I already having the results. I'll be showing them. So you can see the foundation report. So this report will also get generated automatically. So let's say, for instance, I already ran the analysis. So we'll run the analysis, and in the meantime, I will show the results in some other model. Yeah. So let's get the analysis run. So it only takes 1 or 2 minutes. So you can see all this two analysis cases are completed. Third case is also completed. Yeah, so what we are doing is we are running a PY nonlinear analysis. So from this analysis, what we do is we are going to get the nonlinear springs, as well as we can get the stability checks of your piles. So once you get the analysis, you can analysis results, you can take the springs from your SoilWorks to your Civil. So how we can go, how we can take it, we will see it now. So let's say in the very first case, this is abutment 3 by 3 of length 13 meter of your pile. And we got horizontal displacement along the length of your pile. Let's say this is your pile. Whichever pile you're interested in underneath the abutment, you can choose. So the corresponding shear forces, ground reaction moments, and horizontal displacement will be automatically generated. So now what you do is, let's say we are going for center, and you got displacement like around 8 mm. It's very less in terms of your 13 meter length of the pile. Let's say we go for this is your lateral displacement, horizontal displacement, which I'm showing you. Yeah. Now what we do is, so we have already modeled it, and now we are going for 10 meter length of the pile. This is about second length, and in the 10 meter length of the pile, you got around 10 mm horizontal displacement. So if it is coming under your criteria, and then that is fine. If it is not coming under your criteria, then we can go for 13 mm pile, 13 meter length of the pile. So that is your first case. And now, as I said, we will be getting the nonlinear springs. So in order to determine the nonlinear springs for each and every pile, what we do is we go into the very first thing, that is we first trail abutment. We go into pile displacement and member forces, and for the 1-1 pile. So let's say we got first pile, 1-1 pile, and this is your 1-1 pile for your abutment, underneath your abutment for the length of 13 meters. So let's say the very first pile, we are having the nonlinear spring like this, and as you go down, your nonlinear spring varies, and this is how your nonlinear spring variation is as you go from top to bottom, and your values will also change. Now the main important thing is you got the spring data, that is your lateral load versus lateral displacement. And what we do is, let's say this is my bottom. I'm going for 13-meter length of the pile. This is my bottom PY curve, and I got the values. I will just copy them, Control C, and you can also export to Excel as well. And you can directly open the model with your piles which is modeled, and you can directly provide a point spring. Let's say multilinear. I will choose a function with the name, let's say abutment bottom node, and I will just say Control V. So you have just copied your spring data in your SolidWorks, and you are going to paste it in Midas Civil. Just press OK. Yeah. So now close it, and we have given the name of abutment bottom node, and you select the bottom node of your 1-1 pile. Let's say 1-1 pile is this one. I just press apply. So your pile will be applied with the particular nonlinear spring, and that nonlinear spring has been obtained from your Midas SolidWorks by running nonlinear analysis, PY nonlinear analysis. So that's how we can get the nonlinear springs from SolidWorks, and we can able to provide them in case of civil. Since this is this is infrastructure project where you'll be having a huge load coming from the superstructure, you'll be having very objective of getting the lateral load behavior of your pile. So in order to determine the lateral load behavior of the pile and the corresponding analysis and design, we need to apply the lateral springs. So in order to get the lateral springs, we need to run the PY nonlinear analysis, and that PY nonlinear analysis has been made in the SolidWorks. That is what this complete main agenda of this particular session. And here we can even find the stability of your different foundations in this particular model as well. So we can have the pile maximum displacement and member forces. So for 1-1 pile of your abutment, you got a maximum vertical displacement of, let's say we will change it into mm, maximum displacement of around 0.005 mm. And similarly, you can have the displacement in X and Y direction as well. The vertical force, you can find it. The maximum shear forces, you can find it. In the total length of your pile, these are your maximum forces. You'll be having maximum moments on your piles as well. So let's convert into meter. So this is how you can find, let's say the maximum value which you obtained in a 1-1 pile is around 56 kilonewton meter. And similarly, you can have the displacement of your pile head displacement at the very top. You can have the vertical displacement, you can have horizontal displacements, you can have vertical reactions, horizontal reactions, and rotational reactions as well. And for the same pile, you can get the different ground reaction, shear force moments, and horizontal displacements as well. So this is your complete data regarding to the first trail of your abutment. Let's say now we go to second trail of your abutment, and we got a maximum maximum horizontal displacement of like around 1 mm. So what we do is we go for pile member forces. So here the total length is like around 10 meter. And what we see is we got a different nonlinear spring in when we compared with the nonlinear spring of 13 meter, because this 10 meter pile is being resting in the weathered rock and not the soft rock. So that's why your nonlinear behavior is changed. So what we do is, let's say if you are going for modeling of 10 meters in terms of like your 10 meter piles in civil, then you can able to copy your spring data in SolidWorks and paste it in the Midas Civil. Otherwise, you can go for 13 meter length again. And since we already generated the bottom fiber soil spring. We can even generate the top fibers and the middle fibers as well. You just copy it, and this is at a 4 meter from the top. We are just copying it, and what I do is I'll go to the software. I will add the function. This is at the 4 meter from the top. Just press. So we got another function. Okay. Yeah. So 4 meter from the top, and let's say selection from the top. So this is each one is your the division is of a 1 meter interval. So this is my particular pile. So what I do is I will just unselect all the data, and this is my particular pile. Sorry, this is my particular pile. Yeah, so this is in X direction, and then press apply. So you got your nonlinear springs at 4 meter from the top. Similarly, you got all the data from your displacements, your vertical reactions, your moments, completely done using this particular module, and you're also finding PY nonlinear curves in addition. So this is the main advantage of your SOILWorks. Now what we do is we go for, till now we have checked for abutment. Now we will go and check for the pile. Piers underneath the piers, and we got a 2x4 piles. So here you can see this is your 2x4, and this is your pier. This is your pile cap, and this is your pier, and here we got piles. So in the piles, we can find the maximum displacement like around, it's very low. We'll see it's like around 0.05 mm in one pile, and it goes and reaches like around 0.5 mm in terms of 3-3 pile. So the 3-3 pile, yeah. So this is your maximum displacement which you are finding. It's almost reaching 1 mm, and when we go for second trial, it is almost reaching, so that it is going on to the negative direction, and it is maximum in the positive direction. Similarly, you can find the moment as well. And this is how you can get the results for different piles, and you can copy over in the SOILWorks, and you can paste it in the Midas Civil. And this is all about the nonlinear springs, which I was specifying it and focusing from the very start. And now let's get back to the presentation. Yeah, so basically we have modeled your abutment and underneath the foundation. So we have modeled the pile and underneath the foundation. So we had chosen two different types of length, that is your till 13 meter and till 10 meter. Likewise, you can go for 12 meters, or we can go for 10 meters, 9 meters as well, so that optimistic result based on the results we can find, and we can proceed for the design and analysis and design in the structural software. Similarly, you can do number of sections, number of your parametric study. So basically what you're doing is you have modeled the complete model using Midas SOILWorks, and you got nonlinear springs that can be taken to Excel, or else you can directly copy and paste in your Midas Civil software as well. This is whenever you post the complete data, this is all the nonlinear springs that will get developed. And for the stability assessment, you can go for the like the results of your vertical displacement, horizontal displacement, and the horizontal and vertical reactions of each and every pile. So that's how you can get even the maximum displacements, vertical displacement and horizontal displacement in each and every pile as well. Based on this, you can assess the stability of your structure. If it is surpassing your criteria, then you need to change the pile like a group. It might be now the spacing will be even lesser and number of piles even more, or else the diameter of the pile is more. So based on the results, we can able to get to the conclusion of the dimensions of your model. So this is very simple. Even the structural engineers can able to find it very handy. And now in the very last case, we will be going for numerical analysis and to determine the stability of your abutment. So this is the different steps which we follow. What we do is we can directly import the model from the CAD. So if you're having the abutment with the different layers, we will import them from the CAD. We'll create the surfaces. We will assign the mesh, and we will assign the properties and materials, and we will auto mesh them. Nothing but we will create the mesh sets, and we are going for subgrade reactions. We will assign certain coefficients basically. And yeah, so this is basically the workflow, and this is a composition of modeling. This is my abutment, and I got piles, and I'm modeling soil as a continuum in here. So I got different layers: the landfill layer, weathered soil, weathered rock, and soft rock. And you got abutment, and you got piles. This is my composition. So we'll get back into the SoilWorks software, where you got a ground module. Yeah, so whenever you're having all this data in the AutoCAD, or you can in any CAD files, you can directly copy over there, and you can right click and paste over here as well. That is one thing. Otherwise, you can directly go into import, and you can import your DWG or DXF file, because not only the design and analysis, but also the stability when it is getting executed, because how the soil is going to behave, we can only find it when we go for numerical modeling. So this particular analysis will show you the behavior of the soil when you go for the abutment and the pile definition, and what is the load acting from the top. So we will directly see it from here. So what you do is you go and import your AutoCAD files. Let's say I'm importing my AutoCAD file. So my file got developed. So it got imported. And again, with one click, so this is my smart surface. So whenever I click the smart surfaces, I will be having all the surfaces developed. And what I do is I'm having a landfill layer in the top, and this is my weathered soil, this is weathered rock, and the last one is weathered soft rock. So what I do is I will import the materials. So I'm having a database in here. So this database will serve you as a reference. If you're not having the geotechnical data with you, you can choose this one because this serves as a reference. And let's say I'm going for a landfill layer, weathered rock, weathered soil, and I can even go for some class 1 rock like that. So you can choose the type of soil layers based on the geological classification. You're having a gneisses, you're having granites, you're having certain schists as well. So now we are going for moculum material, let's say. You just save and assign them. So all will get generated in the like table over here. So for the landfill layer, these are the properties that were considered, and this data will be given by the geotechnical engineer. Otherwise, you can choose it from the database. So for the abutment, I have considered the like a concrete property. So that is your modulus of elasticity of 2e⁻⁷ in kilonewton per meter square. Yeah, this is my material properties, and for structural properties, I'm having a pile. So this pile is of 1 meter diameter, and let's say this is my length of the piles, and length of the piles has been directly modeled in the software. So we choose the shape, and we choose the section. Let's press close. So this is what we are defining. So let's say my material is concrete. I can directly use the concrete. Otherwise, you can define your own material over here. Close it. So we have defined the piles, we have defined the layers. Now what we do is we need to assign the layers. So let's say this is landfill layer, this is also landfill layer. I will just drag and drop. So whenever I drag and drop, I'll be having these surfaces underneath the, so like your landfill layer. So 1, 2, 3, 4, and 5. So all these 5 layers are underneath the landfill layer. Similarly, I need to do the same for the second layer, that is your weathered soil. Just drag and drop. Similarly, third layer, drag and drop. The fourth layer, drag and drop. So we will cross check them whether we are going to have the similar surfaces. So when I check the weathered soil and selected the surfaces, this is being highlighted. So this particular layer is being given with the weathered soil. Similarly, select the surfaces, you'll be having weathered rock and so on. So similarly, you need to assign the structural property for your piles as well. What you do is you go for a curve, you choose the curve. So you choose the curve. So this needs to be given with the pile property. So we got a structural property beam and just drag and drop. So I have already assigned it, so we'll select it. So these particular lines are assigned with the pile property. So now what we do is we are done with the modeling. We need to mesh them. So what we are doing is we are having an abutment, we are having a piles underneath it, we are modeling a continuum soil, and we will apply the load and we'll see the behavior of the soil because of the load coming from the your superstructure. With one click, this is your smart mesh. Let's say I will choose a fine mesh and press OK. When you press OK, you'll be having this particular mesh that will be generated automatically. So this is your smart mesh. And now we need to apply boundary conditions. So just with one click of your smart support tab, you will be having all the supports getting developed. So this is your smart support. And similarly, we need to have a load. Suppose let's say you're having a load. So go to pressure load, let's say, and your bearing is resting over here. I'm choosing my loads in here. This is my first. So let's say my load is of like around 200 kilonewton per meter square from the top of the superstructure. I will just press OK with the load setting. So now here the load has been applied. Similarly, you can even apply the nodal loads if you're having any pre-stress load because you can apply the pre-stress loads to your anchors or all the cases. So if your anchors are needs to be modeled in this particular case, you can even model the anchors because sometimes the abutment cannot able to resist the entire active at pressure from the backfill or from the soil. So what we do is we need to attain we need to execute some anchors as well in that cases. So this particular software can able to model the anchors, and for that particular anchors you can have a pre-stress load as well. So that's how, and what you do is you're done with the meshing, you're done with the boundary conditions, you have applied certain load, and what you do is you need to go and run the analysis. Go to analysis case, add. Suppose let's say I'm having all the mesh sets. I need to activate all the mesh sets, and I'm activating the boundary condition, and I'm activating the load. Let's say abutment stability analysis. So in order to apply the loads in increments, you can apply the number of load steps as, let's say, 50. So your load is of like 200 kilonewton per meter square. In each and every increment, 200 divided by 50, that is your 4 kilonewton per meter square will be applied. So in order to determine, in order to study the soil behavior in detail, we need to apply the increments, like how the behavior is changing. Is it still in plastic zone, or it is in elastic zone with this particular load or else? So that's how we need to check it. So just press OK and press OK. So we got analysis, and I already run the the abutment, this particular analysis case. So you can directly go and run the analysis. Now I have already ran the analysis, so I will show you the results. So at each and every step, I have applied 50 steps, right? So at each and every step, I can find the results. So in the last step, we will see the displacements. Yeah. So what is the maximum displacement? You can see how it is varying, and also you can find the deformed shape as well. Yeah. So you can see this is how the abutment will deform based on the load that is being applied, and we will see the maximum and the minimum results, and what is the value I will be seeing it now. I will change this into mm. Yeah, it is very it is very low, and it is coming under the criteria. The maximum is of 0.13 mm in the positive direction. Minimum is nothing in negative direction. It is of a 0.35 mm. So you can find it on the top of your abutment and all along the length of your pile, length of the soil as well. And apart from this, you can even get the forces in your beam, in your piles. Basically, I'm going for axial forces. Let's say what is axial forces on my piles, the maximum and the minimum. Let's go. Yeah. So the maximum load which you're finding is like around 133 kilonewtons on your pile, and the minimum is like around 19 kilonewtons. And now we can even find the bending moment diagram. So this is how you can find the bending moment diagram when it is in contact with the soil. So what we are doing in earlier is we are modeling soil as a springs, and we are getting the bending moment diagram. But in this particular model, the soil is in direct contact with the pile. So that's how you can get the bending moments in your particular pile as well. So when you apply the pile element, you can even find the skin friction which is acting from top to bottom. So you can find the ground element status. So what it basically represents is the plastic with the red color. So whatever the soil underneath your abutment is going into plastic zone. That means it is displacing in the higher, the displacement of this particular soil underneath the abutment is very high, and it is going into plastic zone. And there is some tension failure all along the length here. Here it's basically the tensile show. Similarly, you can get the stresses as well. The stresses in the abutment plays a key role, right? Because that will be helping you in finding the stability of your abutment. So let's say we will find the total stresses in x direction, that is your in x direction, let's say in total direction. Here you can see the load is being applied onto your abutment, and we'll see what is the stresses onto your abutment. And yeah, so here you can see from the top, in the very top, you can find it's a 258 kilonewton per meter square of your stress. It's too high, but if the criteria is well underneath, and that is nothing but your material can able to take that particular load, then this is safe. Similarly, you can find the very minimum load in the top, and in the bottom you can see, because the piles are transferring the load towards the bottom, and you can see how it is increasing towards the bottom. So that's how you can able to see the results. And now I will show you the results for at the maximum strain. Basically, this plastic strain will provide you with the failure zone, what is the zone where it can get failed. So you go for equivalent plastic strain. So you can see this particular area is like a failure surface, and this can able to form a failure surface, and that's how the shear failure surface will be forming. This is your one particular case. And now what I will be doing is I'll be having a stress versus strain diagram, and we will like a stress versus displacement or stress versus your strain, whatever. We will see how that can able to, what is the shape of that particular stress versus strain. Let's say I'm going for like a soil underneath your abutment. I will go for displacements, let's say vertical displacement. Not vertical reaction, we go for vertical displacement. So all the steps here at this particular point, let's say underneath your soil, and we will be having a graph. Yeah, this is how it is almost linear. You can see almost linear, but it's not a complete linear based on the number of increments. If the increments is even higher, you will be having the non-linearity coming into the picture. So your like like you can even export into Excel. And similarly, you will be having your nonlinear behavior based on the load coming into your from the superstructure, and the soil can able to behave as a linear or as a nonlinear. That depends on the load. Yeah. So you can draw the stress versus strain behavior. You can see the settlements. You can see the vertical displacement. You can see the abutment stresses. You can see the pile element forces like axial force as well as beam forces. And this is about your ground model. And as I discussed, this is about your foundation model. So from the foundation module, you basically getting the nonlinear springs, and that nonlinear springs can be very much helpful in order to determine the forces in your pile in realistically way. And you can find the changes between the linear spring as a nonlinear spring, because at a very low loads there will be high stiffness onto your pile from the soil spring if you use linear spring. But if you use non-linear spring for a very low load, there will be low resistance, because it's a non-linear behavior of the soil comes into picture when you go for non-linear spring. So that's why non-linear PY, non-linear analysis is must and should for very important structure where the load coming from the superstructure is very high. So that's it from my end. Now we will go through the different